G of t is a derivative. It says it's the rate at which, in tons per hour, at which the unprocessed gravel arrives at a plant. So it's unprocessed when it arrives there, and then we're going to process it at a rate of 100 tons per hour. That means we're like organizing in the bins or something like that, right? So it's coming in so fast, and then we're going to process it. Now, g prime of 5 is just your derivative of this function right here. Here's your g of t. So g prime is just your derivative. Mathate that function in the graphing calculator. If you forgot how to do that, watch your graphing calculator video. Now, since this was in tons per hour, that means this is a derivative of that. So that's going from like velocity units to acceleration units, which would be tons per hour squared. And that just means that rate of change, that g, is decreasing at that rate of 24.58 tons per hour squared at that t equals 5 hours there. Letter B just says find the total amount of unprocessed gravel that arrives. So the key word there is arrives. I don't care what was already there. I don't care what was, leaving out. I just know how much, I just want to know how much arrived at the plant during hours of operation, which is in between 0 and 8. So that's just a straight math 9, that G of t. Remember, the G of t is in tons per hour. So when I integrate that, that will just give me tons. So you just mathate that function because that's the arrival rate. Mathate that. That's the total amount that arrived in that time period. Letter C, I have two ways to work that out. I'm just going to talk about one at the beginning, then we'll do letter D, and then I'll talk about the alternate way to do letter C. Letter C says, is the amount of unprocessed gravel at the plant increasing or decreasing at time t equals 5? Show the work that leads to your answer. All right, so here's what I did first, is I saw G of 5. I simply took the 5, plugged it into the G function, gave me this 98 number, tons per hour. This is how fast that the gravel was arriving at the plant. That's how much, about 98.141 tons per hour is arriving at that plant being unprocessed. But it tells us we are processing that at a constant rate of 100 tons per hour. So my thought process was, I was just trying to use some common sense. Or if it's coming in at a rate of 98 tons per hour, but I'm processing it at a rate that's quicker than that, that means the total amount of unprocessed gravel is actually decreasing because I'm processing it quicker than what it's coming in. So I just kind of reasoned that out a little bit like this. So I said, hey, the amount being processed is 100 tons per hour, so more of the gravel is being processed than that unprocessed gravel is arriving at the plant. So that's why I put the amount of unprocessed gravel is decreasing at t equals 5, since the amount being processed is greater than that unprocessed amount that's arriving there. Okay, so hopefully that makes sense. If that was a little weird, let me do letter D, and then I'll show you an alternate way to do letter C there. Now, letter D says, what is the maximum amount of unprocessed gravel at the plant? Now, this is one of these problems. We got to take into account the total. Got to get an equation for the total. Now, when you do the total, I think it was like on the 2003 or 2005 test, it was the sand problem on the AB or something there, but we did a total problem here where you got to take into account what was already there, what arrived at the plant, and what you like processed already, right? And so it tells us at the beginning, the plant has 500 tons of unprocessed gravel. So that's unprocessed. And then when I integrate that G function in between 0 and some time, that gives me how much arrived, how much more of that gravel arrived at that plant that was still unprocessed. And then we're processing at a rate of 100 tons per hour. So I just did like a minus 100t. And then a little technicality. So this is our total equation for the total amount of unprocessed gravel. Little technicality. Notice I got an X and a DX here because we've seen stuff like that before where the letters, they don't need to be the same, all right? I don't think it's a huge deal if you put G of t, dt right there just to be real technical. They should be different letters. My mind says when I integrate this, it'll have X's in it, but then I'll plug in that t and I'll have that t variable that I want right there. All right, but so that's the total amount. And so we'll see more like that in the future as well. Now, when this says the maximum amount, minimum amount, and you have a closed interval, this is a 3.1 absolute extrema problem, which from your blue packet, what we'll do is we'll make an XY chart, and we need to check the endpoints and the critical numbers. And they'll have on their rubric, if you're not checking all valid candidates, you won't receive full credit for that. So here's my whole work for letter D. So I was making an XY chart or an XA chart, and I already put in the endpoints of my interval, and then I got to find any critical numbers. Critical numbers we know is where that first derivative is equal to 0. And so I took the derivative of this thing. The derivative of that was 0. The derivative of the integral is just going to be that inside part, and the derivative of 100t was just 100. And I set that equal to 0. So it was this equation minus the 100, set that equal to 0. You're supposed to graph that into the graphing calculator and then hit the window button, make that your x min of 0 and your x max of 8, and it'll graph that function, and then you use that calculator to find the x-intercept to find that 0 in there. If you forgot how to do that, watch the graphing calculator video again, and I show you how to do that. But that's our critical number, and you're trying to figure out the maximum amount. And so they told us at 0, it was 500. Now at 8, we started, I'm plugging into this equation up here. So it was 500 plus the integral between 0 and 8 minus 100 times 8, because it was 100 tons per hour you would process that for 8 hours. So 100 times the 8. And then this is the answer that we actually came up with in part B. So I already had that down. I didn't need the calculator for that. I was able to get that number. And then I did the math 9 with this stuff in the calculator. I did 500 plus the math 9 of that G function just with that. And then I did minus 100 times that 4.923 number in there. So you kind of see my arithmetic there, and it was a calculator problem. So then you're going to get that, and that's the maximum Y value. So that's going to be what they ask for. Now, if it says what time does that occur, that would be your 4.923 seconds. But it says what is the maximum amount of unprocessed gravel, and that's going to be that 635.376 tons. Now, if you kind of like that approach, because we have to kind of get that down for letter D anyways, going back to letter C, you could start with that equation, that total amount, what was already there, what arrived, what we processed. That's your total amount equation. And then letter C was asking, is that total amount increasing or decreasing? So then you could take the derivative of this. The derivative of that is 0, the derivative of that is the inside, and the derivative of that is 100. And then they said, is it increasing or decreasing at 5? So then you could take A prime of 5, just plug 5 in for the G, and then minus the 100, and you get this negative 1.85 number. And then since that derivative of that total amount equation is decreasing, that means, I'm sorry, that derivative is negative. That means the total amount of that gravel is decreasing at that T equals 5. So if you like that way better for letter C instead of this, then go for it. But we need to kind of group together some of those and just practice those total type of problems, because they're not the easiest in the world. Treetop.